Okay, well, let me say hello to everybody out there, out on the internet. It looks like we've been getting thousands of viewers, which it always boggles my mind because even under the best of circumstances, one gets, a few hundred students in an MIT classroom. But so having thousands of viewers on the internet is pretty exciting. Today's lecture is, as always, showing off what programming languages can do, but also we're going to have a lot of fun. You'll see here we're going to play with some of these image transformations. We're going to do stuff like this and like this. And what my real goal for this lecture is, how do I say it? There are math courses out there like multivariate calculus and linear algebra, and these are basic college math courses that many people take. Probably, maybe you've already taken such courses, or maybe you're going to take such classes in the next few years. Maybe you're an expert on these subjects, or maybe you've never, done these subjects before. It's my belief that whether you haven't seen these things before or you are the expert, there's nothing like doing it on a computer. So let me start showing you a few things. And the title of today's lecture, I might as well go to the top here, are Transformations and Automatic Differentiation. That's abbreviated as AutoDiff. Right? So AutoDiff technology is a very, very exciting technology that has really come to its own in just the last few years. And it continues to amaze me what we can do with it. But to set the stage, what I'd like to do is scroll down, and I'm hoping you can join me and do this along with me. And let's just play with a few transformations just to get the idea. So I've got a bunch of transformations predefined, like a general linear transformation. You'll see what these words mean in a minute. A shear, a warp. Here, look, I'm going to put this one down on the bottom to do it last. Okay, a rotation, and so forth. So here, you could take any picture that you like. Here's a long corgi. We could do the usual corgis. You could pick a picture, or you could load any one you like from the internet. We also have this arrows picture, which this is really has been our test pattern. But here, how about let's take the three corgis. Okay, so here's a picture, and what we're going to do is we are going to run a linear transformation, this general linear transformation, by picking the coordinates of this matrix. So this is what's called the scrubbable matrix. If you're running it in your own notebook, you can click here, and then you could see, oh, look at those corgis, becoming sheared, right? You might notice, what happens to the squares? Does somebody want to tell me? The squares become parallelograms as you shear, right? So this is a shear. We could do other linear transformations, right? And we can also zoom in, zoom out, zoom in from the top left, just disappear. So you've got a whole lot of controls. It's actually very easy to make these sorts of things. So here, let's put these back to maybe around 1 so we can play with it later. Okay, so this is a general linear transformation, right? And quite frankly, this is really how you should look at matrices, in my opinion. So all too many people think of matrices as arrays of numbers, right? It's just like a table, like you could be looking at a spreadsheet. It's just a boring table of numbers, and there are all too many linear algebra classes which would have you think that linear algebra is about doing like row operations and column operations on those tables of numbers. And you would never walk away with sort of the intuition as to what a matrix really is. Okay, but as far as I'm concerned, this is what a 2 by 2 matrix is, and this generalizes to 3 by 3 and n by n matrices. So we'll say more in a bit. But one point of this lecture is, what is a matrix? If you thought it was a collection of numbers, if that's how you've thought of matrices all your life, here's your chance to really find out how the big shots think of matrices, right? It's this kind of linear transformation. Okay, so we'll say more about that, but let's play with a few more of these while we're at it. So here, let's pick. I've already played with a shear, so there's the shear. A pretty fun one is a warp. So here, let's do a warp. A warp. Here's the warp, and let's warp these poor corgis. There they go. Look at that. So this as you might imagine, here it's like, you see, we could put the corgis through the washing machine just like Photoshop could. So this warp is a nonlinear transformation. Okay, and so these are the sorts of transformations that you don't see in a linear algebra class because, in a pre-computer age, it was really hard to sort of see these things in real life. I mean, you could draw them one pixel at a time, but it would have been really, really hard.
Alan, could you zoom in on your browser, please?
Do the zoom in. Let's do that. All right, that's a good idea. The trick is
a bit more.
Well, I need the alpha in screen, so I don't know if I can do that.
Okay.
So this is about as far as I can go and still be able to manipulate. I could try to do one more, but let's see if I can make this just okay. I can do one more level. Okay, there we go. Right. So here are the warped corgis, just to sort of see this image. We have a few other images. For example, composed images where, for example, you can, well, here, let's rotate the corgis first. Let's rotate the corgis. There they are, right? So now alpha controls the rotation. I guess that's a pretty easy transformation. This one's linear, okay? And then we can compose things. For example, we can do a rotation followed by a warp, right? And right, so here it is spinning around. Here's
so,
another.
Can you, you can actually hide that, the markdown input. How do you, can you mention how you can visually distinguish whether a transformation is linear or not?
Well, I would like the students to think about that for a moment.
Okay.
Right, and if somebody wants to tell me in the Zoom chat, they can tell me. Okay. Yeah, definitely zooming in really helpful.
Or on Discord.
Or on Discord, that's right. Think about, what makes it seem linear versus nonlinear, and then we could talk about what that means. All right, so I just wanted to set the idea of, just to kind of get things started. I mean, I could have shown this later in the lecture, but I kind of wanted you to sort of see two-dimensional transformations, linear and nonlinear ones, right away. Okay, we have a couple of more. Maybe I'll bring them out. There's the XY that we have floating around. So this is a very strange transformation. Okay, and one more transformation that I have floating around. You could define your own, just write your own function. But the R theta transformation is yet another one that we have floating around, which is kind of fun to look at. So this is the one where it sort of fans out. Let's see, got to zoom a little bit. All right, so point number one is transformations, linear and nonlinear transformations. Okay, so like I said, my goal is to kind of get you to see linear algebra and multivariate calculus in new ways. And I really believe, I would love to hear your opinions after this lecture, but I really do believe that you can not have taken a course, see it here in Julia, and you already get the intuition, or you could take the class first and get better intuition from this lecture. And I still believe that even the experts, even the people who think they know everything about multivariable calculus and linear algebra, still get something about being able to manipulate these things in real time. So just because you understand these things, it doesn't mean that you can't further solidify your intuition. All right, so that was like a little bit of the trailer from the movie. Now let's go ahead and start the lecture for real. Okay, so we're going to learn a little bit about Julia. We're going to learn a little bit about modern computer science all at once, as usual. Okay, so let's start with some very simple things. Okay, let's remember last time we defined linear combinations of images. You remember that we scaled an image by multiplying by a constant. We also combined images by adding the colors in each pixel. And we said that if you do combinations of these two operations, you get linear combinations in general. Okay, now today we're going to see linear combinations from another view, but let's start with really, really simple, almost high school stuff. Okay, functions in math and in Julia. So I wrote down a couple of univariate functions here. There's the square function, the sine function, and a generalization of the square where you have x to any exponent alpha. And in Julia, you can express these in a number of ways. And so I just thought I'd show them to you. There's the so-called short form, where you say f of x is x squared. Okay, and just to follow the subscripts of the math, just want to show you that if you go here, let's just do it, right? So you see it. If you go f backslash underscore 1, and then I'm going to hit the tab key, I get the subscript 1, right? Or I can go 7, right? And I get the subscript 7. So this is one way to make your code look more like mathematics, right? I mean, I suppose I could have written F1, but, you know, and I see people writing alpha like this as opposed to writing it like this. And it seems like a telltale sign that you're on a computer and you're not doing math anymore. So here we blurred the distinction between math and computing by actually writing things in a nice way. Okay, so back to function calls, I can create the function x squared simply by saying f1 of x equals x squared, and then you can see f1 of 5 is 25. Okay, so that's one way. That's the short form way of writing a function. And the short form, as you might expect, is a handy method for defining a function when it's not a very complicated function. When you know, when you can do it with one expression or two, that's usually when you use the short form. Then there's the so-called anonymous form. Okay, and you know, any Lisp people out there, this is sort of these lambda expressions, but nowadays they're generally just called anonymous forms. And so here, instead of giving it a name like f2, the word anonymous means there's no name, right? It's the function is the thing that takes x to sine x. Okay, that's it. The function doesn't have a name. It's just the thing that maps x to sine x, right? And so you could take this thing and evaluate it at pi over 2, and that'll evaluate, of course, the sine of pi over 2, which is 1. Now, of course, I can go ahead and give it a name. It won't be anonymous anymore, right? I could say my sine is this function, and then I can go ahead and evaluate it at, say, pi over 2, and of course, it'll work, right? So I got 1 out. Okay, so this is anonymous. Okay, but then I give it a name, right? Okay, good. So we have the short form for a function, anonymous form, and then there's the long form, which you've seen before a few times now. You take a function and you have an end, and you put in the return value. You don't have to type the word return, but it makes it very easy to read. And I just sort of threw in another piece of the puzzle that you can have a default parameter alpha equals 3. So the way this works is if I evaluate f3 of 5, it'll take the cube. Okay, so the exponent alpha is understood to be 3 if I don't tell you what it is. But if I do include it, then that's what it'll be used, right? So 5 squared is 25. Okay, so so there's f3, and let me also mention rather quickly that the concept of a keyword, because they come in handy. So instead of a comma, we use a semicolon, and then what that means is that you have to type alpha equals if you want to know what exponent is being used, right? So this way you know the keyword, or maybe it would have been good to call this exponent, for example. That might be even more readable. Oh, can I not? Oh, sorry. Let's wait. What did I do? Wait, what can I do that? All right, you know what? Let's leave it as is. Okay, and so when you call it, you go alpha equals whatever you want it to be, and it runs. Okay, so 3 different ways to write down functions, maybe not that exciting, but they come in handy, the short form, the anonymous form, or the long form. Each one has its uses, each one has its places. When you write Julia for a while, you start to know which ones to pick. Meanwhile, it probably doesn't really matter. You get to pick your choice. You could see Julia's function documentation for more. Okay, but let me get into the more interesting thing, which is automatic differentiation. So that's the big hot topic. It got really hot because of machine learning. So in some sense, automatic differentiation's been around for decades. I mean, I know people who were doing it 20 or 30 years ago, but more and more these days, people are applying it in so many ways, and the programming languages themselves are letting you do things with differentiation that, in a way, in a way, calculus. I don't know. I feel like you almost couldn't have imagined it. So to get the story straight, uh, let's actually run it first. Okay. So just to check that we know what we're doing. So we're going to use the forward diff package. There's also something called backward differentiation, but we'll do that another time. So I'm just going to grab the forward diff package, and I'm going to just start taking some numerical derivatives. Okay, and so F1, you might remember, was x squared, right? So let's remember that. Remember, F1 was x squared. Okay, so the derivative is 2x. So if I evaluate the derivative at 5, I should get the number 10. That's good, okay? And let's also remember here that this is the same as saying the derivative of x cubed is, of course, 3x squared.
Alan, could you zoom in a bit again for now?
Zoom in some more. Okay. Let's see that. Maybe even one more time.
Yeah.
Good idea. Thank you. In this particular notebook, I may have to zoom in and out depending. So, you know the usual trade-off. If I'm looking at just one small piece, then I could zoom all the way in. But if I need to sort of see a bunch of things at a time, I'll have to zoom out. So I'll try to work with that. Right. So 3x squared, 3 times 5 squared is 75. All right. No big deal. I'll tell you what is a big deal. What is a big deal is this derivative is being calculated in a way that's different from what almost everybody expects. I think that's what's the big deal. So when you think about differentiation, you probably think about how you learned it, right? You probably learned all the rules. I mean, there aren't that many rules, and it's very, the derivative of sine is cosine. The derivative of product is UDV plus VDU, right? You learn a bunch of rules, and then it's pretty mechanical to evaluate derivatives. Okay, I call that symbolic differentiation. It's the sort of thing that Mathematica is really good at. You can do it in Julia as well, but we're not going to do that today. My point is, this is not what is happening here. Okay, it is not like the way you did calculus when you took a calculus class. Okay, so if it's not that, then you might think it's like what you do in a numerical class, or sometimes people do this in calculus where you do a finite difference, right? You evaluate your function over a little bit, you subtract it from where you were, you divide by your displacement, right? And that's your, that's an approximation to your slope, and so that's probably what's going on here, right? And many people would guess that. And interestingly enough, that's not what's happening here either. Okay, what's happening here is a different kind of thing. And if there's time at the end of this lecture, I'll tell you a little more about what's happening. But for now, what I want you to walk away with is that computers are taking derivatives now in new, exciting ways. I mean, the ways have sort of been known for years, but it's happening on a large scale now. And it really lets you do things that I think people had no idea they can do. So it happens a lot with machine learning, but in other places as well. We'll see in a minute more. But right now, I just want you to walk away with the derivative of a scalar function. All you have to do is write down the function and where you want to evaluate the derivative, and bump, it happens. Okay, and I decided to do a numerical differentiation with finite differences just to kind of show you. I've got a little epsilon. So when epsilon's So here I'm going to take, in case you never knew what a derivative was, this is how it would be done in a math class. Again, this is not how forward diff is working, but just to give you the equivalent mathematics, if I wanted to know the derivative of sine at the point 1, right? So, I mean, this sort of syntax tells you what I'm doing. This says, give me the derivative of sine at the point 1, right? This we know is the derivative because we've taken calculus classes. And this is that finite difference thing where you move over just a little bit compared to where you were. You know, this is the delta y over the delta x sort of thing. And you see that if epsilon is very large, like 0.1, all you get is like one digit, 0.5, right? But if you move your epsilon to be smaller, you get, you know, better and better digits, as you'd expect, right? So, and at 10 to the minus 6 to the displayed number of digits, it looks like it's matching perfectly. Okay, but I mean, in some sense, this is the intuition of what the derivative is. And of course, something magic is happening here in how you're calculating it. Okay, scalar functions are easy. That's just the warm up. You all knew that. Let's move on to what you might see in a multivariate calculus class, right? So that the MIT number is 1802. MIT has these funny numbers for all of its classes. And as far as I could tell, only undergraduates and the professor of the course knows the numbers for the classes, right? So undergraduates know all the numbers, and the professors know the numbers for the courses they teach. That's what I've learned, right?
You
And
said you don't know the numbers of the courses you teach.
yeah, and I have a peanut gallery in the background telling me that I don't even remember the numbers of the courses I teach after a couple of years. Okay, so let's talk about multivariate functions. Again, this is a simple idea from multivariate calculus. Let's define a function f5 of x, which is which is a function of 3 variables. Let's just say. Okay, so hold on a second, just to okay. A function of 3 variables. So I mean, I just picked a random function. It has no meaning. 5 sine of x1 times x2 plus 2x2 over 4x3. Okay, and in Julia, we kind of have a choice now. I mean, I guess in math you have a choice as well, but you don't think about it as much. We could actually write it as a function of a vector. So this is how you would do it, as a function of a vector, right? And so this is the short form, right? And it says, oh, input a vector and then pull out the components, right? So here are the x1, x2, and x3 components, right? Or I guess I'm calling it V now. V1, V2, and V3 components. Or what I find more readable is you can write it as a function of 3 arguments. But then the drawback of this is that it doesn't apply to vectors, right? So you could write it as a function of 3 arguments or function of this is definitely more readable than this. I think everybody would agree with that. But in practice, what you really want to do is take functions of vectors. So I'll show you how you can fix that in a minute. But here's sort of a kind of halfway step, which is that go ahead and write it in the readable format. Here, I'm going to call it F6 now, just to give it a new name. You can go ahead and write it in this readable format. And then when you want a vector, you can just go ahead and call it on that, right? And so Julia lets you do that. Julia says that it's okay if you call this thing with 3 arguments, this is the function that's called. And if you call it with 1 argument, this is what's called. It's kind of very, very handy to be able to have a function dispatched just on the number of arguments, right? And so this way you can, you can kind of write a bunch of different methods for the same function, and and it'll kind of work in both ways. And so you could see here that where's the, you don't see the code, but I can call it with 3 arguments, or you remember from the first lecture, this is how you define a vector. So here it is f5 applied directly to a vector. Maybe a little space here would emphasize the point that this is the vector function and this is the 3 scalars function. Okay, and so here I'm doing the same thing with f6 just to show you that it's working. There's a trick, by the way, that lets you define it all to do it at once, where you can actually have readability and it works for vectors. And I debated as to whether I should show this to you on the 3rd lecture of the course, but I thought it was worth showing you because it just makes code much more readable. So here, this double parentheses, which basically means a function of a tuple. So this is a kind of a Julia thing. But don't worry about like how it's working. Just point out that this, when I write this, it is readable, right? X, Y, and Z, just like math almost. But it actually takes vector arguments. Okay, and so you could write one function that's readable and has vector arguments, just in case you want to do that. Okay. Getting back to the function f5, though, in fact, maybe I should have moved this up a little bit. Let's go back. I'm going to move this back to here because this was as good a time as any to show it to you. So in Julia, this f5, you might say, well, is it this function of 3 arguments or is it this function of a vector argument? Well, if you call methods of a function name, you can see that it's actually, this is a little bit ugly to read, but you could see that for methods of f5, you see there's a 1 argument version and a 3 argument version. So if you compare that with, I'm almost afraid to do this, but if you go methods of plus, you can find out that there's a very large number, almost too many to admit to. Plus is so overloaded that you can't even see these things. You can add matrices, you can add vectors, you can add numbers. You can add booleans, you can add reals to floats. So all of these different things come up in add. Again, more on another time. Let me have to find the end of this now. It just goes on and on. There it is. Yeah, so I'm just going to get rid of that. Okay, but the bottom line here, whoops, let's go back up here. The bottom line is really just a few different ways of writing functions. Okay, so where are we on our table of contents? I have to move the Zoom thing to kind of see this. All right, so, hey, where's my table of contents? My table of contents disappears.
It doesn't show if you're zoomed in too much.
Oh, I guess that's clever. I see. So that's the down part of zooming. I see. One lesson, there it is. Look at that. Okay, so where were we? We are talking about scalar valued multivariate functions. Okay, and now what I want to do is talk about derivatives of scalar valued multivariate functions while I'm at it. Okay, so let's get some derivatives. So where are we? Okay, so there's this word gradient. Again, maybe that's scary to some people. Maybe some of you, have been calculating gradients for many, many years now. But if you have a scalar function and you calculate the gradient, whatever that is, the gradient is just the derivative for functions from vectors to scalars. It's really all it is. It's the derivative of the function from. So if I evaluate this f5 function, where was its definition? It's up here. It doesn't really matter what it was defined to be, but here it is. 5 sine xy plus 2y 4 over z, whatever it was. You evaluate it at a vector now, and you get a vector output. Oh, here's the reminder of what it was. Okay, and again, this is not how automatic differentiation works, but just in case you didn't really catch the intuition as to what a gradient is, or if you never saw it before, this little box of code is all that you need to get the intuition as to what a gradient is. Okay, so you might remember my epsilon from earlier. Okay, so all you have to do is, we have a function of 3 variables. Okay, all you have to do is perturb the first argument and compare it to where you started. Okay, and so this is like a delta, the change to the function over epsilon for the first argument. Then you do it for the second argument. So the epsilon is here, and here you do it for the third epsilon, the third argument. Okay, and then the gradient is just the vector that combines all of these. And you can see that, here, let's make it vertical. You could see that whatever it is, whatever magic the automatic differentiator did, it gives the answer to enough decimal places to be convincing, right? I think this was an 8, but it's pretty convincing that this is what it is. And perhaps I'm repeating myself, but I feel like it's a really important point. If you take a multivariate calculus class, you probably practice taking gradients, and maybe you're good at it. But still, for me, there's something wonderful. I mean, maybe it's just me. I don't know if I could share this with with the internet audience out there and the MIT students that are here, but there's just something really nice to just see, oh, I've changed the X a little bit. I've changed the Y a little bit. I've changed the Z a little bit. And I get the same answer that the magic gets, right? So for me, I love seeing these things. Again, if I could share that joy, okay? But I hope certainly that that this numerical thing makes the idea of a gradient more intuitive. And what's happening left and right these days is machine learning, also other optimization contexts, where everybody wants to optimize scalar functions of many parameters. In the machine learning world, this is called the loss function, and everybody's following the negative gradient. So what you do is you've got a function, a scalar function, and your goal is to make that function as little as possible. So you start at a certain vector, and you start at a point, and you compute this direction, and you go a little bit in that direction, and you do it again and again and again. And this is sort of the simplest way to minimize functions, probably also the best way when you have many variables like machine learning. When you only have a few variables, I'm just going to say that there are much better techniques than following the gradient. But these days, people have so many variables, you can't really afford to do the fancy techniques. And so you do the simple technique of following the gradient. Okay. All right. Well, I think you see where I'm heading here. We did univariate functions. So that's, scalars to scalars, right? A number to a number. And then the next two, we did vector in and scalar out, right? So this is scalar in, scalar out. This is vector in, scalar out. And now for the big boys and girls, let's go vector in and vector out, right? That's where the action is, right? So vector valued functions, vector valued multivariate functions. So what goes in is a vector and what goes out is a vector. And here are the functions, some of which I displayed at the very beginning of the lecture. But here you could see a bunch of functions, some of which have parameters. And they're all designed to work on vectors. Okay, so here, let me actually make that very clear. All the functions below are designed to work on vectors of size 2. Maybe I already said that. I may have actually already said that, but can't say it too many times. All right, so let me just sort of show you a few functions. There is the identity function, the world's most boring function, maybe next to the zero function. The zero function might be the world's most boring function. This is the do nothing function, okay? You put in the vector xy using the trick I showed you earlier, and out comes the vector xy. All right, here's an example of a typical linear function. There's nothing magic about the 2, 3, minus 4 coefficients, but this is your typical linear function, okay? Here's the scale in the x direction by alpha, and notice that what's going on here, I now have a function that has a parameter, alpha, okay? And so, but that's okay. Scale x alpha is a function that takes a vector and scales that vector by alpha in the x direction. And of course, scale y of alpha is another function. This is a function, right? It's not the value of a function, it is the function. Like, it's not like sine of x, it's like sine. It's not like exp of x, it's like exp, right? This is a function that if you give me a vector xy, it'll scale the y direction, okay? And then this is called a rotation. It takes xy and rotates it by theta degrees. All right, this is the format. This is the shear, which also has a parameter alpha. Okay, and then alpha kind of is sort of the strength of the shearing. And then this is the general linear transformation where I just have any coefficients ax, by, cx, and dy here. Okay, so just to show you that if let's do this slowly. Rot pi of 2 is a function, right? It's generic function with one method, right? It's just a function. Until you call this on an argument, like 3, 4, it doesn't do anything. But if you rotate 3, 4 by 90 degrees, you'll get 4 minus 3. Okay, so now I'll bet that you noticed that some of these functions, I should have said some. Let's make that some of these functions. That some of these functions could have been defined with matrices. So if you've taken a little bit of linear algebra, this actually shows up at MIT in 1802, even before our linear algebra class. You might have noticed that we could have, instead of writing this out in this sort of long, clunky form, mathematicians have come up with matrix notation to, right? So it becomes a matrix times a vector, or in math, it looks like this, right? And so there's something kind of nice about this notation, because instead of breaking up the coefficients all over the place, it kind of separates out the coefficients, the things that matter for the function, and the vector xy. Okay, so let's see. Oh, these are all linear, actually. Let me see. This one's linear. They all could be, yeah. Every one of these functions could be written with a matrix, a 2x2 matrix. So I take it back. All of these. We bet you've noticed that all of these, I shouldn't have written that, because all of these have been defined, could have been defined with matrices. Okay, but then if you remember the warped Corgi from earlier, that one can't be defined with a matrix, so we actually have to spell it out. So there's the warp, there was that r theta, and those xy functions, and you can't write those with matrices, but they're still vector to vector functions, right? That's all that they're still. These are nonlinear functions. Okay, so but they still take vectors to vectors. So the warp function might look a little complicated, but it's not really very complicated. I'll explain why in a minute. But what you do is you take the distance from the origin of xy, and you use that to multiply your angle, and then you rotate. So what's going on is your rotation depends on not only your parameter but also your argument. Okay, so there it is. There's the warp. Some of you might recognize that the r theta and xy are the typical conversions from polar coordinates to Cartesian coordinates. I think many of you will have seen that in high school, or maybe later. I don't know. They used to do this stuff in high school. I don't know if they still do these things in high school. Maybe some of you could tell me if they still do it in high school. But these are the conversions between polar coordinates and Cartesian coordinates. I wanted, as long as I was talking about cool ways to write functions, I would like to mention sort of another way to write the same function that kind of is fun in Julia. And again, these are the sorts of things that you might have to look at like 5 times before you see what's going on. But once you learn how to do these things, you could do it yourself, and you start to realize in the end how elegant Julia can be. And so, for example, if I wanted to write a warp function and I didn't care whether the input was a vector, right? So you see that we see that warp depends on a parameter alpha, right? And an input argument xy, right? So let's not worry at first about the format of the inputs, and just do this flat, and just do this with a flat structure. But that is, yeah, let's just do it with a flat structure. That is just, let's just look at alpha, x, and y, and we see that because we've already defined a rotation, we can create the function that rotates by the parameter times the distance to the origin. So this would work, except that it is not it doesn't take a Julia vector as input. It takes 3 arguments. Okay, but no worries. We now know what to do. We can define the function to be the anonymous function that takes a vector and applies the thing we just defined and does it at the point that we want to do it at, right? So you put x and y twice, because in this case it actually defines the r, and then here it applies it. So if you got that, great. If not, just walk away with the notion that there's some fun things you can do, and you can see that it actually, I just want to check that it works, that the warp function that I wrote the long complicated way and the warp 2 function that I wrote like this give the same answer. So just to show you that it's correct. Okay, now the big fun. Automatic differentiation of, I'm going to call these things transformations. You see, I think the word transformation, I almost feel like I should look this up. But what's the difference between a function and a transformation? Probably nothing, other than how the words are used. I think a transformation, I think we use the word transformation when the input and the output are both multidimensional, right? Otherwise, I don't think we call them transformations. When like a scalar function to a scalar function might technically be a transformation, just like a square is technically a rectangle, right? But you don't say rectangle when you mean square, right? You just don't do it. So in the same way, you don't say transformation when you mean a function, right? And I don't think people use the word, I mean, we could check. I'm sure that I could say these things and somebody will find counterexamples, but I haven't seen transformation used a lot for vector to scalar. I think vector to vector is, or high dimensional to higher dimensional than one is where these things go. So let's, the word for a higher dimensional derivative is Jacobian, right? So in a way, the vocabulary is derivative, that's elementary calculus, gradient, that's what you get when you go from vector to scalar, and vector to vector, the word is Jacobian. But they're all Jacobians in a way. They're all the same thing, just kind of generalized. But here, let's take the warp of 3. So the warp has a parameter. So let's take warp of 3. I don't think I need a 0.0. So let's just kill that part. Let's take warp of 3, and let's find its derivative at 4, 5. Now remember, warp takes a 2-vector in and takes a 2-vector out. Don't forget that. So warp takes a 2-vector in and a 2-vector out, and before you know it, the derivative of warp at this point is a 2-by-2 matrix. It's got 4 numbers, okay? And again, if you don't, maybe you never saw a Jacobian, maybe you don't know its mathematical definition, or maybe you do. But here it's easy to see the definition. What we're going to do is we're going to take the warp function and we're going to evaluate it a little bit more than the first argument and then subtract that for the value at, right? So this is like any derivative. You're going to do it on the first argument and then we'll do it on the second argument. Okay, and maybe it's worthwhile to look at the pieces individually. So here's dw dx. Okay, and we'll make it vertical to be suggestive. Okay, remember that if this function takes a 2-vector in and takes a 2-vector out, right? That's the thing you got to remember. So this thing here is a 2-vector, and I'm going to subtract a 2-vector, right? And so the result's going to be a 2-vector, and look at that. That's the first column of the Jacobian. Okay, and of course I can get the second piece of the Jacobian, and you'll see that this thing is the second column, okay? And of course, you just concatenate the two, and you get this 2-by-2 matrix. So from a mathematical point of view, this is what a Jacobian is, okay? And again, some of you may already know this. I still love seeing it numerically. I just love being able to see that, I could just do this difference, and there the answer is. Okay, so let's get back now that we've sort of played a little bit more, and let's see here. I'm afraid, Dave, I know you're going to want me to zoom, but I think I need to be able to play with these parameters, so I have no choice. I guess I could move this. Yeah, I'll tell you what, just to get a little more real estate, let's go back and play with this again. So I'm going to do the general linear transformation, and I'm going to move this below the picture. Yeah, let's go here. Let's go below the picture. But anything else I can do? Maybe that's about it for now. Let's just rerun this code to make it the identity. Okay, so can I? Yeah, so I can change the pictures to the long corgi, right? Or corgi.
You can remove the text, rerun this cell.
Yeah, that would be a good idea. Let's do that. Yeah, let's get rid of that. That's not doing much good, is it? There we go. Show grid lines, don't show grid lines. Okay, so here I'm going to repeat what I said in the original lecture, the beginning part of the lecture. choosing a matrix chooses a transformation. This is how I would like you to see matrices, right? It's a matrix is a transformation. When people tell you how to do matrix times vector, they're actually telling you where you can take every pixel is a vector. Oh, you know what I could do just to kind of make the point? Yeah, I can draw with my zoom pen. So here, let's give you an example. Let's take I don't know, the tip of the middle corgi's ear, or I'll do this point here. I would call this point 2, 3, right? So 2 over and 3 up, and not quite the tip, but here I am on the corgi's ear. Okay. Now, if I go and apply a matrix to that, I'm going to do matrix times vector, right? And I'm going to get a new point, right? So A times 2, 3 is going to be an image. Now I'm slightly lying to you, and Dave's going to catch me because I'm actually inverting the matrix, but let's not worry about that. Vector, see, so one matrix times vector would tell me, I don't know what it'll show up to be, but depends on the matrix. But here, let me just sort of draw a picture that lets you kind of imagine what it would look like, right? So this is going to be A23, right? This is the place where the image ends up. Okay, so this is like 0, 1, 2. It's like you have a flattened coordinate system. Okay, and so all matrix times vector is doing is it's taking it's not doing, you see, a transformation is not one matrix times vector. You do it to the entire picture all at once, right? Every point in this picture has a coordinate, right? And then when you squash things, here, let me clear this now. When I start moving my matrix around, right? Every point, the entire image is going to another place, right? So it's not one matrix times vector, it's the matrix times every vector, every point that you have here, okay? And this is what a linear transformation does, okay? And so does somebody want to tell me how you could look at the grid lines and tell me if the transformation could be written as matrix times vector? Right, so if somebody does it in Discord.
Yeah, there was a response on Discord.
Do you want to read it or say it out loud, Dave?
Straight line in input goes to straight line in output and vice versa.
Okay, so
that's sets of points that are collinear remain collinear. Right.
So all of those things are true, but that is actually not enough. So if it's, I could promise you that if you don't have that, then your your transformation is not linear. However, that alone is not quite enough. For example, if you had a situation, for example, let me draw a situation where, suppose your grid lines started to do this. So the rows are equal, but so this is 0, 1, 2, 3. I think you could organize it that all the lines. Actually, I'm not completely sure what would happen to the non-vertical lines. Maybe they would stretch in funny ways. I just don't think that's completely enough. Well, maybe it is. Maybe I'm wrong. Let me just think. Actually, it might be enough.
I don't think it's enough.
I have to think of a counterexample.
Bilinear transformations.
Yeah. All right. Well, now I got to think. I won't do that in real time. Can't think while I'm on live television.
I mean, there's also affine transformations, which.
Yeah, but let's not worry about affine transformations. Anyway, that's not the answer I'm looking for. Whether it's correct or not, I have to think. Did anybody else give an answer?
There was another one, which was, they have to stay equidistant as well.
Yeah, that's almost what I'm looking for. I kind of wanted a 2-word answer. Maybe I'm just. So what I'm looking for is the grid lines become congruent parallelograms. That was kind of the answer I was looking for. I'm not sure that the other answers are wrong. They're probably right, but the way I wanted to say it was congruent parallelograms, right? So all of these have congruent parallelograms, right? And so that's what makes it linear. Okay. So And while we're at it, some of you might know there's this thing called the determinant, right? And so if you have a matrix, just to remind you, if you have a matrix that's A, B, C, D, there's this function called the determinant, which is AD minus BC. And in linear algebra classes, you learn a lot about how the determinant tells you whether a function is the matrix is singular or not, whether you can find an inverse. But how many of you learned that the determinant is how the Corgi's nose is scaled, right? And so to be clear, let's go back to the zero. Let's go back to the identity. So let's get this to the identity. So you see you could take any, there's nothing magic about the nose, obviously. You could take the ear of this Corgi, right? Here's his ear, and you can call that area before transforming. Okay, and then you can apply a transformation. Oops, I gotta do it this way. You apply the transformation, come on. And now the ear has been transformed to a new place. Maybe it's gone here. Oh, come on, let's do it like this. Okay, so here's the ear now. This matrix has determinant 1, so actually even though it's been warped, it's actually been sheared, the area remains the same because this matrix has determinant 1. But the determinant in general is the scaling factor, right? So if you take area after over area before, any area you want, as long as it's any area you want for a linear transformation, that is the geometric interpretation for the determinant, right? So that's usually, I think that's much more interesting than whether a matrix is singular or not. All right, I'm about to run up against my microcentury. So let me just see what else I can tell you quickly before, we could do a little bit more of this on next Monday. There are a couple of things. I'm lying about the matrix. It's actually the inverse of the matrix that matters. And it's if I go ahead and make, I think I need more time, so I'll probably pick this up on Monday. But I just wanted to mention that if you have a nonlinear transformation, you've got parallelograms when you look closely enough, but they're not, when you start going out, they're not congruent anymore. But locally, in a small neighborhood, every function is linear, and then the determinant Jacobian will tell you how areas scale. So I'll say more about this on Monday, but if I can just run the T, if I could find it again. Where's my T? T. Where did I do it? I can't see it now. Did I move it? Choose an image, center. I think it's below the image. All right, I've lost it. Never mind. What I was going to do is I was going to warp this thing. Don't see it anymore. I was going to warp this thing and then show it to you, but we'll do that on Monday anyway. For those of you who want to do things before Monday, if you'd like to know, I told you automatic differentiation is mysteriously interesting. I made a 10-minute video about this a couple of years ago. All right, it's really 11. And you might just want to take a look at it because it'll really show you the difference between how you learn calculus and how a computer can calculate derivatives these days. Okay. I also made a few comments about more than 3 dimensions. You can read that on your own if you like. All right, so what I'm going to do is say goodbye to the folks out in internet land. The MIT students are welcome to stay on if they would like to. And we'll be back on Monday with more fun things that you could do with Julia, math, and computational thinking. Okay, now, Dave, who has the power this time? Who's the host? I am. So let's stop.